Hello everyone, welcome back to the past paper discussion. In this particular video, we are going to discuss a 27 mark question from paper 3 of AAHL. So let's dive into it. And this question is based upon investigation on curved surface areas and how the calculus techniques are going to be used here. And we're going to derive a basic key formula in geometry, but we have memorized those. Now this is a kind of derivations over here. Let's start. And here you can see y is equal to mx is a line given. A part of a line we are going to take from 0 to h, and m and h are positive constant. Now, when this particular line is rotated 360 degree about the x-axis. So like this is a fixed point and we're going to rotate the line. So the line will be here, the line will be here, here, here. So when I rotate 360 degree, I will get a nice cone structure, right? I'm just making it. So we will get a cone, right? Now we have to derive the surface area of the cone is directly given to us. It will be of the form 2 pi integral over h y root of 1 plus m the whole square dx. So this is for any 360 degree rotation through x-axis. If you do, this will be the thing. Now for my cone, if I substitute, I will get a surface area of the cone, right? So first part. So this is the basic understanding of the first part. And here, if in this case, m is 2 and h is 3, show that area is equal to, that means A means surface area is equal to 18 root 5 pi. Okay, we can copy that because we are going to find A, right? And let's take it. Let's use it here. And wherever m comes, we can use 2. Wherever h comes, we can replace it with 3. So we got 2 pi. And what is 0 to just over h? It's 0 to h, right? And y is mx, right? So I can put y is equal to, what is my m? 2x. So y can be replaced with 2x. And m and stuff are already given. M is 2, h is 3. So let's replace whatever possible here. Like m, h and y, we're going to replace. So y is 2x into square root of 1 plus m square. M square is 2 square and dx. We can take the constant out, 2 pi, and the 2 is a constant. Then this one also constant. When you solve this, it's root 5. So root 5 and 0 to h. Oh, we can replace the h too, right? Let me replace the h as 3. So 0 to 3. Here also 0 to 3 and x dx. It's a very simple integration formula. Let me show you the formula booklet for your reference. Here we go. So when you integrate x power n, this is the formula we're going to take, right? Okay, so for me, it's just x. We can treat it as x power 1. Let's take this formula and switch to the solution page. Here we go. And that's a simple formula. So let's do. So what is integral over x? If you treat it as x power 1, it's x power 1 plus 1 by 1 plus 1. That's it, x power 2 by 2. So same thing we're going to do. So this is equal to 2 pi. Okay, so we have this, right? So 2 times 2 is 4. 4 pi root 5. 4 pi root 5. And then integral 0 to 3 x. I know integration of x, it's x square over 2 divided by, okay, x squared over 2 and 0 to 3. We need to apply the limit. So 4 pi root 5 into 3 square by 2. And 1 2s are 2, 2 2s are 4. This is 2, this is 9. 9 times 2 is 18. 18 pi root 5. We have started with A. and we end up with 18 pi root 5, which is exactly what they are asking for, and hence we have proved it. Right? So that's simple. First part is this is the proof. Very simple understanding based question, and we can move to the next. Now we are going to consider a general case. Y is equal to mx is given here. We are going to form a cone by rotating the line y is equal to mx, where 0 less than or equal x less than or equal to h through 360 about x-axis. Now we are going to solve three particular questions under this. Right? So first, in this case, you write an expression for r in terms of h and m. Okay, so this is rotated, right? So when you rotate it, you will get a cone like this, and which will act as the radius here. R is radius. Okay, so which is acting as radius of this cone is r, and this is acting as h. Exactly, this is the circle we got, and this will be the radius of the circle. Right? And let's move forward. So when you take this particular triangle, this is the height of the triangle. So this particular is height. This is acting as radius, right? Let me take this out, and we got a right triangle over here. And from the origin, this is h units. From this, it's r units. So any point here at the end point can be written as h comma r. So h comma r lies on y is equal to mx. At the edge it lies on. So we can substitute. This is your x, this is your y. So I will get r is equal to mh. So I expressed r in terms of h and m. That's it. The problem is over here. And this carries just a single mark. Now we can go for the next part. And it next is a 2-mark question. Slant height in terms of h and m. We have to express slant height in terms of, this is your slant height. We can take the same diagram over here. Okay, here we go. This is your slant height in terms of h and m particularly. So this is a right triangle, right? So L is hypotenuse, and we know L is equal to square root of r square plus h square. Right? Basic Pythagorean theorem. Okay, they are asking L in terms of h and m. H is okay, but r we need to convert. We already covered r in terms of m and h. We can use. So square root of mh the whole square plus h square. We know that r is equal to mh. Correct? Right. And moving forward, we can substitute L is equal to square root of m square h square plus h square. Take h square common. So square root of h square into square root of m square plus 1, which is h square root m square plus 1. L is equal to. Right, this is L in terms of h and m. Right, and next part. Hence, by using above integral, show that A is equal to pi RL. Right, let's try to prove it. So given integral, the very first integral they have provided is A is equal to 2 pi integral 0 to h y square root of 1 plus m square dx. So now let's substitute. What is y? It is mx. So 2 pi integral 0 to h is h only. This is a general case. And y is equal to mx square root of 1 plus m square and dx. Okay, m is a constant, right? So m root of 1 plus m square, we can take it out. So equal to pi m into square root of 1 plus m square, take it out, 0 to h x dx. Again, the same differentiation technique from the formula booklet, we can use it. So when I integrate it, 2 pi m into square root of 1 plus m square, x square over 2 integral 0 to h. And we can substitute it now. So 2 pi m square root of 1 plus m square. We got h square by 2. 2 will get cancelled. So pi, and we got this m root 1 plus m square h square. But we are aiming for pi RL form. And we know that we have proved it actually. R is equal to mh, L is equal to h into square root of 1 plus m square. Now, we have to reframe this, that's it. So let me take 1m and 1h together. So pi mh. One more h will be there, right? So that h and the other part, we can take it together. And mh means it's r. We can apply it here. And h into root 1 plus m square is L. So area is pi RL. This is a general case. We know generals of, for a general case, surface area of the cone is pi RL. And we have derived it using geometry concept and calculus, basically. Right? And let's move into the next part. So this is one of the main part. So far we have covered around 10 marks. More than 10 marks actually we have covered. And next part. It is very similar to that. But instead of line, we are taking a semicircle. Right? So let's understand this. We are going to consider a semicircle with radius r. And our semicircle is basically upward, like above the x-axis. It is defined by the equation y is equal to square root of x square r square minus x square, where it runs from minus r to plus r, the domain. This is the diagram provided. First one is find dy by dx based on this. And okay, so this for this description, this is the only thing we're gonna do. And what is our y? It is square root of r square minus x square. We can find dy by dx using the chain rule. Right? And let me show the formula booklet here. Okay, so chain rule. Y is equal to g of u, and that u is a function of x means. So this is the chain rule. And there is also another simpler way. So if you want, you can use this. All right. So let's move it to the solution page. Here we go. Okay. So you first write in a differentiable form. This surd symbol will not help. So this can be written as r squared minus x squared, the whole power half. First, work on the power. So dy by dx is equal to, how will you work on power? You will multiply that exponent inside, and then you will keep the base same, and you will remove, subtract 1 at the top. So I work on the power, now work on the base. Differentiate the inside base with respect to x. R square is a number, so it will vanish, 0. Minus x square, when you differentiate with respect to x, it's 2x. That's simple. So now we got half into, this can be written as r square minus x square whole power minus half into minus 2x. We can cancel this 2 and 2. And the negative exponent can be reciprocated. So 1 by square root of r square minus x square. And minus x will be in the numerator. So this is the expression for dy and dx. Dy by dx in terms of r and x. And that's simple. The first part is. Now we can move. This will fetch us 2 marks. Next. For this next problem, a description is given. A differentiable curve is defined for x1 to x2 and y is greater than or equal to 0. In this case, Yeah, the same case. When any such curve is rotated 360 degree about the x-axis, of course, a 3D solid will form and it will have a surface area like this. 2 pi integral x1 to x2 y into square root of 1 plus dy by dx the whole square dx. We can relate that with the straight line example. Straight line we have slope. For other curves we have dy by dx. So that's simple. Now, a sphere is formed in this case by rotating a semicircle. So this is a general description, whatever I have given in red. Now relating with that semicircle we have solved previously, right? If you rotate that semicircle, in this case like about 360, about x-axis, right? You will get a sphere. And in this case, you have to show that surface area is 4 pi r square. We know very well surface area of sphere is 4 pi r square, but we are going to derive how it works, right? From the calculus part. So let's start. And we have this direct things given. But we need to work on, in previous problems, it's quite easy to find the bound, right? The boundaries, upper bound and lower bound. And y is, we have dy by dx also, we have it. So let's go. So y is square root of r square minus x square. We have dy by dx, just in the previous case, we have solved it, which is minus x by square root of r square minus x square. Then what we need? Okay, what is this x1 and x2? It is nothing but the x-intercepts of the curve. The curve intersects the x, right? At which place that is what. So it's very clear. It is running from minus r to plus r. So this is your bound. x1, x2 is, let me write here. x1 is minus r, x2 is positive r. Right? And that's it. Let's write the formula. It is given in this particular, whatever they have given, we have to use it. So that is integral a is equal to 2 pi integral x1 to x2 y into square root of 1 plus dy by dx the whole square and then a dx. Let's start substituting over here. So this is equal to 2 pi integral from minus r to plus r. What is my y? This is my y, right? So square root of r square minus x square into another square root 1 plus dy by dx the whole square. I know dy by dx. So what is dy by dx the whole square? Let's calculate it here. Dy by dx the whole square is minus x, when you square it's x square. Denominator is a square root, so the inside stuff will remain the same. And let me take this completely and put it over there. So this is x square by r square minus x square. And then a dx is there, right? So it's 2 pi. Okay, we can do one thing here. Whenever there is a property of an integral, if your integral is running over minus a to plus a, like f of x dx something, this can be reduced as 2 times integral 0 to a. So that will be easy, right? If it's 0, the substitution will be easy. So we can use this property, and without property also we can solve that. Is not a problem. So 2 pi, one more 2 I introduce, and integral will now range from 0 to r. Square root of r square minus x square times, when you simplify this inside stuff, square root of r square minus x square plus x square in the numerator divided by square root of r square minus x square and then dx. These two things will get cancelled. So I got 4 pi integral 0 to r minus x square plus x square cancel, and I will just get square root of r square is r and then a dx. R is also a constant, right? Let it be out. 4 pi in r integral 0 to r dx. Right? And moving forward, it's a basics differentiation. So when you different integration, when you integrate dx, it will become x, and bounds we need to mention. So 4 pi r r minus 0, which is 4 pi r square. We are evaluating, actually we are deriving surface area of a sphere and we got the same. That's simple. We have solved this part. Right. Now moving forward. E part, the description is the same function from minus r to plus r. If your y is equal to f of x transformed into y is equal to kx. So inside a k is multiplied and it is greater than 0 means it's a horizontal shrink with a scale factor 1 by k, right? And let's go. So how to this? Okay, first one is very basic thing. What is the geometric transformation? So we know that when the k is greater than 0, the transformation is f of x to f of kx. And if your k is greater than 0, we can say it's a horizontal. Whatever inside, it's horizontal. And multiplication means stretch or shrink. If you mention stretch, the scale factor it's going to be the reverse of it, 1 by k, right? And or you can say horizontal compression with scale factor k. So this is fine. Stretch is the most common used word. We can go with that. Now write x-intercept of f of kx in terms of r and k. Okay, we know f of x, but we need to work on f of kx and then we need to find the x-intercept. So let's go. Okay, f of x is square root of r square minus x square. F of kx is square root of r square minus k square x square. Right? In place of k, I will replace x. So kx the whole square and this go like this. Now x-intercept means what? F of x is 0. So square root of r square minus k square x square is 0. And what is x? Correct? So r square minus k square x square is 0. R square equal to k square x square. X square is r square by k square. And x is equal to plus or minus r over k. Right, so these are my x-intercept. Now third part. For y is equal to f of kx, find dy by dx in terms of r and k. Yeah, that's simple. If your y is f of kx, that we know already, r square minus k square x square, find dy by dx. So let's write it in this form, differentiable form. This is also differentiable, but easy to differentiate. Whole power half. And the same, apply the chain rule. Half into r square minus k square x square whole power half minus 1. What will we do first? First work on the exponent. Done. Then multiply by differentiate the base. R square is a constant, it will become 0. So minus k square is a constant. It won't vanish because it is associated with x. And x square will become 2x. That's it. So minus k square times 2x divided by minus 2. And this one can be written as r square minus k square x square whole power minus half. We are going to take it to the denominator and this is how it will continue. Here we can look. So 2 to cancel, minus minus cancel. We got k square x divided by square root of r square minus k square x square. This is all. So this is my dy by dx in terms of r and k. Right? So that is the simpler one. And moving forward. Next one. Semi-ellipse y is equal to f of ks is rotated 360 degree about the x-axis to form a solid called an ellipsoid. Express surface area in terms of r and k, and our expression should be like this: 2 pi integral x1 to x2 under root a polynomial dx. Right? So let's get started. Okay, we are working on a semicircle Okay, right? Semi-ellipse. So what is a semi-ellipse here? Whichever I just f of kx is the semi-ellipse, right? Semicircle, when you just dilate it, it will become semi-ellipse. So my function is going to be, my y is square root of r square minus k square x square. We already work on x-intercept. That is important. Function and what are the bounds? So the bounds are minus r by k to plus r by k. Right? And next part is, that's it. We can start differentiate and we want dy by dx also. So dy by dx, we just now got it, right? K square x by this. K square x by this one we can copy, k square x by r square by square root of r square minus k square x square. And right, let's go with the surface area formula. A is equal to 2 pi integral the inputs, that is the bounds, minus r by k to r by k. And then y. What is y? R square minus k square x square into square root of 1 plus dy by dx the whole square. So it will be k power 4 x square by r square minus k square x square. This thing is actually dy by dx the whole square. This is y and dx over here. Let's continue. So 2 pi integral minus r by k to r by k square. It's very similar to what we have did, but here we have an x, that's it. Now you solve inside a big square root. It will get multiplied here, r square minus k square x square plus k power 4 x square divided by r square minus k square x square into a dx. Solving it further, 2 pi integral minus r by k to r by k square root of r square minus k square x squared, actually I missed it, right? And into square root of r square minus x square. If you take common, you will get a k square minus k power 4. That's the thing. But denominator is square root of r square minus k square x square. And this will get cancelled. Now the simplified form is equal to 2 pi integral minus r by k to r by k square root of r square minus x square into k square minus k power 4 dx. So 2 pi x1 to x2 and under the root there is a polynomial dx. This is our surface area and we have represented in the same format they have asked for. Right. And we can move further. Now, the fifth case is, it's very interesting one. Planet Earth can be modeled as an ellipsoid. So we have just modeled an ellipsoid and it's like surface area for an ellipsoid. Our planet Earth also can be modeled in this way. And we have some important tips given here. Axis of rotational symmetry runs from North Pole to South Pole. The distance from North Pole to South Pole is 12,714 kilometers. Diameter of equator is 12,756 kilometers. By choosing suitable values for R and K, find the surface area of the Earth in kilometer. Okay, what is R? It is going to be the radius of the ellipsoid, right? Here, radius of the Earth. And diameter of equator is given, so I can divide it. I can connect the radius with diameter stuff. And K is like, let's imagine this is our Earth like an ellipsoid, not like this, but let's imagine for an instance. Okay, so the dilation is towards the center. So if you just zoom like this, if I zoom here, both the things will get stretched. So R over K will be the better because they set K greater than 0, right? So we can choose the values for R and K in this way. So R by K is our scale factor because we are stretching it, right? And that's it. Now, right. And they are asking for, we have to find surface area of the earth in kilometers square, correct to 4 significant figures. And they want the answer to be expressed in scientific notation, of course. Right. Okay, first let's take our model for an ellipsoid is a 2 pi x1 to x2 y into, sorry, this is the old model. Ellipsoid model is minus r over k to r over k square root of r square minus x square k square minus k power 4. That's it. And dx. So this is our model. Now what is my r and k? That's the only thing we need to fill. So r is, okay, what is diameter of the equator? 12,756. Let's do here. Diameter is 12,756 kilometer. And r is going to be half of it, 12,756 divided by 2. And we will get 6,378 kilometer. This is my r. And next is scale factor is greater than 0. And when we are dilating, when we are zooming it, k will be greater than 0. So let it be r by k. R is the bigger thing here. So k is equal to, we are solving for k. So my k is ratio of radius divided by, and what should I write? Divided by what? And this is, let me quickly model it. The distance from North Pole to South Pole, this is the center of the origin. Sorry, this is not, this is south. Okay, anyways. So this is my radius, and this value will make r over k is the dilating factor. So r over k, that is half of the distance from North Pole to South Pole. They have said 12,714, and half of them, it will be 6,357. Right? So this is how we have to form the k. Right? You can even approximate it by dividing, but keeping this is also good. Right? 3303 and so on. Right. And coming to this context, let's start substituting and integrating that. That's simple. We will get the surface area of the earth. Let's go here. So 2 pi out. Okay, you can use this trick also. Multiply by 2 and make it 0 to r by k. What is r over k? It's 6,378. Okay, r by k we didn't find. Let's do. R over k is 6,378 divided by 6,378 by 6,357. So 6,378 times 6,357 by 6,378. This get cancelled, and 6,357 is the bound we have. So 0 to 6,357. R by k value is, and let's start substituting r square. R is 6,378. Wait a second. 6,378 square minus x square into k. What is my k? 6,378 by 6,357 the whole square minus 6,378 by 6,357 the whole power 4. And we drop a dx here. So 4 pi integral 0 to 2, like 0 to this, everything will come there. And we can switch to the calculator part now. Right. So let's go. Okay, that big integral we're going to solve here. And go to calculate, the normal calculating page. And let's start with 2 pi is out. So 2 pi. And let's go for integration by clicking on it. Integration with limits. So it's 0 to 6357 or 78. Okay. 0 to 6357. And next is the square root and the big stuff over there. So which is here, use control and square root. Okay, there are a lot of numbers, big numbers coming in between. First a fraction, which is 6378 by 6357. Okay, it's just 6378 square. 6378 square, and then minus x square. Minus x square. Then open the bracket, and opening and closing the bracket is very important. Then again open the bracket, and inside the bracket there is a fraction, which is 6378 by 6357 the whole square. Then minus 6378 by 63, the same number, power 4. So go for this, same 6378 by 6357 whole power 4. And then a dx is there. So this is what? Let me check it once. Yeah, and we are differentiating, integrating with respect to dx. And that's it. Let's click enter. Okay, it's actually 4 pi. So let me multiply with the 2 again. So same thing, but 4 pi. Let's go front. Okay, we can multiply one more 2. Yeah, so this is the answer we got. And we can just display that in our paper. Here is a solution page. Here we go. So we got surface area of the earth is equal to 5.10. When you just approximate it, 3101. E power 8 means 10 power 8 kilometers square. So this is what we got. 5.101, 10 power 8 kilometers square. This is the surface area of the earth. And the big problem, investigation problem, came to the conclusion here. So that's simple it is. Thank you so much for listening. So let's meet in next video.